Dear colleagues and audience, and good morning for the local people, and good evening for the foreign people. Welcome to attend Professor Colin McLarty's online lecture on logic and the foundation of mathematics at Wuhan University. I'm Chen Yong from School of Philosophy at Wuhan University. First of all, it's our pleasure to introduce the speaker, Professor Colin McLarty. Is the Truman P. Handy Professor of Intellectual Philosophy and of Mathematics at the Case Western Reserve University in USA. He is the current chair of the Philosophy Department. He is an American logician whose publications have ranged widely in the foundation of mathematics and philosophy, as well as in the mathematics. Is a leading research field and a highly and historian of mathematics. McLarty worked on establishing that Fermat's last theorem can be proven in a setting with much weaker assumptions than the ones used in the Weyer's proof, which makes use of involved category theoretical constructions. Okay, we also glad that we have the interlocutor, Professor Harvey Friedman from Ohio State University in USA. He's an expert on foundation mathematics and concrete incompleteness. And after the main lecture, and Harvey Friedman will give his comment or questions. And also he will chair the discussion session. Our audience are welcome to ask the question during the discussion sessions. Pay attention to that. During the lecture, please mute your audio. And during the discussion, you can open your video to ask questions or post your question in the chat box. Okay, now let's welcome Professor Colin McLarty's lecture. He will talk about what is concrete incompleteness. Okay, now please, Colin, now is your time.
Okay, thanks. Yeah, it was an interesting thing for me to do this. I don't really have an answer. As they say, this is, I like this Chinese expression, problem, wen ti, this is a wen ti, this is not a ti-wen. A ti-wen, I could give an answer, but this is a problem. It's not a question that I can just answer, but it's something I'm interested in exploring. I'm going to draw heavily on work by Friedman and Visser, of course, but I'm also going to compare this to Hilbert's plan. Hilbert wanted a concrete intuitive proof theory like number theory. This is what he saw he was going to develop. There's no problem about translating the word concrete. That's the German word konkret. And intuitive, anschauliche, again, there's just no serious problem. I mean, of course, intuitive is madly ambiguous in every language that I know, but it is the right word to translate Hilbert's, no question about that. What drew me to this is I'm interested in the advances there have been in incompleteness really since the 1980s. A lot of my career, I wasn't following incompleteness, right? I mean, I studied it as a graduate student. Actually, I was talking with some philosophers about some recent work on this, and they were assuring me, well, you know, nothing's really happened in incompleteness in the last, you know, since the 1970s. I was just stunned. I mean, of course that is. And so, you know, I was working on that, and so I want to talk about what's been happening, and the angle that kept pressing itself on me as I was preparing this is that the first and second incompleteness theorems have become more and more concrete in recent decades themselves. Besides the other things that are meant by concrete incompleteness, they themselves, by creating new tools, by putting more stress on fragments of arithmetic, and I name a couple of important ones there, other things, various advances, sort of displacing the technicalities like enumeration of the axioms in favor of relevant features, which are caught by interpretations typically. And I say displacing because this doesn't necessarily get rid of the technicalities, but it makes them less prominent. It puts them less on the face of the results. So the results are in more comprehensible terms. And of course, experts have been comprehending them for a long time, but I mean, making them immediately suggestive to other mathematicians. And in fact, I'm going to look at ways that the new work could change something Harvey has said. I mean, Harvey has said this, and there's very good reason for saying this. I mean, this is a quote from his Boolean relation theory's introduction, relation theory. While it's true that Kahn's EFC can be stated entirely in terms of finite strings of symbols from a finite alphabet, when stated in this way, it is no longer natural in any mathematical sense. And I mean, that's really true by the best established methods. I mean, you could look at a lot of versions of the incompleteness theorems, and that's absolutely true of them. And it's also a good approach for his project there. But I want to talk about how new ideas, often created by Friedman and Visser, they're really making this more direct, so that you really are thinking about strings in arithmetic and other relevant structures. And it's making it more concrete, say, in Hilbert's terms. That's why I'm going to bring in Hilbert. I'm going to say, look, for most of the decades since Hilbert, Gödel, since Gödel proved the incompleteness theorems, they've been pretty technical, but they are getting less so with recent developments. Now, I want to say early on that maybe I am too optimistic about these new ideas. This is not, it's not just a slam dunk. I mean, there are typical current problems that are discussed in the research literature. I didn't get these. I didn't go reading and say, hey, here's a problem. I'm reading and Visser says here's a problem, or Harvey says here's a problem. Results that you'd like for recursively axiomatized theories like PA, because that's what we really want this for, might only be known for finitely axiomatized theories, really only known for sentences. And this won't be because nobody's tried. It's because currently the proofs have only developed to a point where they're good for sentences, or the concepts have only developed to the point where the proofs can be given for sentences. Results you would like to prove by weak means, say Robinson's arithmetic Q. I will be describing what Robinson's arithmetic Q is. So results you'd like to prove by weak means sometimes they need stronger means. Like I say, this is proof in S12 interpreted in Q on a cut. I say apparently stronger means because this does get interpreted in Q. Now, this is technicalities that some of you won't understand, but it's not really obvious that these results are using stronger means, but they're on the face of them, they are. And I would say these are real. This is not that people haven't tried to get past these. People have tried to get past these and currently aren't getting past them. And Albert talks about this quite a lot in his preprints. If they can be solved, it's going to mean genuine new ideas. But of course, new ideas occur. This work is advancing. It's advancing very well right now, and so I'm optimistic that this can work. That we can expect to see Gödel's incompleteness theorems themselves much more concretely than what they were classically. Okay, now this leaves Friedman's project thinking what he generally talks about under the heading of concrete incompleteness. This is a quote. I don't know when he said this, but it was on the farm email list talking about the 70s, early 80s, when he really clearly crystallized the program of getting incompleteness for real good concrete math. Now that remains the work in Boolean relation theory, the work in various successors to Paris-Harrington. I mean, that work is still going on, and it's not changing with the things I'm talking about here. That's still to be done. It will be done. It is going on numerous lines, but that's not what I have anything to say about here. What finally caught me as I'm digging into this was the way that Gödel's first and second incompleteness theorems themselves are looking more and more concrete. And at first, I'll tell you how I thought of this. When I was in graduate school, Of course, I studied the incompleteness theorems. This was in the 1970s, early 1980s, and not with people who were doing the research. So it was a little bit old-fashioned. But of course, I studied them, and they did not look like an algebra book or a differential geometry book. It was just a different kind of thing than learning those parts of mathematics. But starting about 10 years ago or so, as I went back to incompleteness for several reasons, I'm reading these current things, and they do look like an algebra book or a differential geometry book in some ways. I mean, it really is becoming more plainly mathematical itself. And I mentioned some of the ways. Developing the right tools. Instead of just finding ways that work, find the right tool, lay it out, and then you have it to work with. And that's been going on. And I don't mean to say that people didn't try to do that for the first, say, 1930 for the first 70 years of incompleteness, but it took a while, right? It's happening now. It didn't happen at the start. And so I want to look at ways that the incompleteness theorems themselves are becoming more concrete in Hilbert's sense. So I really want to look at Hilbert and how he thinks of mathematics. What I have up here it's an abridgment, but it's I want to say this is the most important thing that's been said in the philosophy of mathematics in, say, 100 years. This is about 90 years old. It's not a fully developed philosophy, but in mathematics, there is nothing we will never know. And not in natural science as a whole, I believe. Our slogan will be, we must know, we will know. There are not going to be unanswerable questions in mathematics. And of course, that doesn't contradict the Gödel incompleteness theorems. Gödel also believed there were not going to be unanswerable questions. They just weren't going to be answered by deducing them from a complete axiom system, because there were no complete axiom system. Gödel and Hilbert both believe that any question we come up with, we will answer. And in pursuit of this idea, Hilbert made a really terrific mistake. I mean, only a genius could have made this mistake as deeply as he did. Only a great mathematician could have seen it, and frankly, only a famous mathematician could have gotten anybody else to pay any attention. And people have been talking this way for a long time. Poincaré even quoted some of them, but nobody pursued it. But this mistake in Hilbert's hands, this led to huge progress. Well, I mean, people know the mistake. But as background to it, Hilbert believed there was going to be no limit to mathematical knowledge. We just saw that. He was a complete triumphalist about that. Any problem that could be solved would be solved. Incidentally, it would be solved in Göttingen. And the solution wouldn't really count until Göttingen had reformulated it. But there would be no limit. Cantor's set theory was going to be a powerful engine for this. Is that famous quote, "No one will drive us out of this paradise that Cantor has created for us." Axiomatics would be a decisive, productive tool. We would give axioms for things, and we would characterize subjects by their axioms. A lot of these axioms would not be foundational. They would be axioms, for example, what we would now call algebras over a field, but also foundational axioms. And those were not mistakes, because these things were already working. Set theory is already working. Axiomatics is already working. If I'm talking about 1930, which I think is about when that picture was taken, and it's when the quote that I gave you was. But here was the really deep idea that we're here to discuss. Hilbert is not going to argue that transfinite set theory is true, because he sees there's no way to argue that. You just can't argue whether this stuff is true. But what he would do is he would justify using it. He would give a purely finite proof that formal transfinite set theory is consistent with finite arithmetic. Incidentally, he already knows that finite arithmetic proves every specific equation on numbers with plus, times, subtract, exponential. He doesn't even bother. He's not very precise in describing it. But finite mathematics already proves every correct equation. So if you have a consistent extension of it, one that doesn't prove any contradictions, then the only finite statements it can prove were already true. So you can use transfinite means to prove finite conclusions if those are the only ones you care about, which they're not the only ones Hilbert cares about, but if the only ones you do, you can still use transfinite set theory and it'll never mislead you. Every time you get a finite conclusion, it'll be right. And in Hilbert's words, he's very clear about this. This scientific demand can, in fact, be met. That is, it is possible by purely intuitive and finite means, just as for the truths of number theory, to gain insights guaranteeing the trustworthiness of the mathematical apparatus. And this is, I'm just even looking at it right now. I mean, this goes real deep in his thinking. He wants this. When he says this demand can in fact be met, he doesn't mean he's met it. He is perfectly aware that he has not produced the consistency proof that he wants, but he knows it can be done. He's sure it can be done. Okay, and again, for people who are worried about the translation, reine anschaulich und finite, that means purely intuitive and finite. Now, what Hilbert means by intuitive, well, what does anybody mean by intuitive? That's up for grabs. That's a point to discuss. What does finite mean? Well, we're not talking about the technical definitions of finite, well, the overt ones. Concrete, inhaltlich, contentual. I would just see that as echoing concrete. So the translations are completely unproblematic. I'll put it like that. What the words mean can be a problem, but it's not because of translating them. Translating them better isn't going to matter. They're problematic in every language. Hilbert believed in infinite sets. Hilbert had no doubt that all these infinite sets exist. But he sees people like Leopold Kronecker, who, I mean, Kronecker doesn't even say these things don't exist. He just makes fun of them. He just ridicules them. Kronecker has no time for these infinitary arguments. And I mean, he's like, he'll talk about Dedekind and what a shame it is that Dedekind's wasting his time on nonsense, because this is just clouds and rain. This is terrible. And he sees that if Kronecker, he can't go and prove Kronecker's wrong. He can't go to Kronecker and say, look, here's a proof that there's infinite sets, because the axioms say there are. That's not going to convince Kronecker. He knows that. But he says, but look, formal proofs in set theory are finite things. Kronecker believes in finite things, right? And let me be specific. Kronecker believes in things that are finite in principle. Kronecker does not only believe in calculations he can actually do. Kronecker does not only believe in concepts that he can actually test for and see. He believes in whatever's finite in principle. As long as it's somehow finite, that's good enough. And Hilbert wants to say, yeah, but these formal proofs, they are finite things. I could show this to anybody, any follower of Kronecker, and they'll have to admit I'm right about this. They're finite strings of symbols. Kronecker can't deny the proofs. He can deny that they're talking about anything, but he can't deny that they're there as proofs. And Hilbert sees that some mathematicians say, well, we can't justify knowledge of the infinite. In fact, Kronecker, says you don't even mean anything by it. So they're not going to use it. He's not going to use the infinite in some parts of his mathematics. Now, Howard Stein has pointed this out. Kronecker freely uses infinitary methods in geometry and mechanics. That's fine with him, only not in analysis, not in algebra. There he wants strictly finite. Others use the infinite without justifying it, and you can read these things. They're quite, I mean, they're very odd to me. They'll use the infinite without justifying it. They'll just say, oh, this is purely formal. This is purely symbolic. So we can just do these things. And when we ask, well, why would you believe the answers? They say, oh, we do believe the answers. Everybody does this. And that's where Hilbert is going to outdo both of them. Hilbert's going to outflank both of those groups. He's going to justify the formal rules by a proof theory. I'm surely he didn't make up that word. The word has to have been around, but not meaning anything like he meant by it. He makes up this idea. We're going to show that the formal axioms are consistent with themselves, and thus they are consistent with all correct finite mathematics. And since finite mathematics is already complete for finite questions, the formal rules can only produce truths when you get a finite conclusion out of them. So that even the Kronikarians will have to admit, yes, we can use Cantor set theory. We'll just only pay attention to the finite consequences. Any finite statement that can be proved using transfinite means will be correct as finite mathematics. And even just now, as I'm presenting this, I'm trying to feel, I mean, this was really hot stuff for Hilbert. This is an exciting idea. It's a fantastic idea. He believed that finite strings of symbols, like formal proofs in set theory, because they are finite strings of symbols, that these are somehow intuitive in a way that infinite sets are not. I think most of us believe that. This is the intuitive domain. And he believed that he could eventually prove what he knew he hadn't proved yet by intuitive finite means, that the finite strings of symbols that count as proofs in formal set theory, because you can define which strings of symbols count as proofs, they can never end with any false statement about finite things. So you can rely on them. Absolutely. Now, Hilbert also believes the infinite statements, because why wouldn't he believe the infinite statements? Go read Dedekind on ideals. These things are too beautiful not to exist. But if you don't believe in them, don't worry, you can still use them. Any finite conclusions you get will be true. So he could prove that all of set theory is trustworthy, even to someone like Kronecker, who believes only the finite part is real. But it's all trustworthy, even if only the finite part is real. So it's true, formal proofs are finite strings of symbols. Absolutely overt, couldn't be, nothing to argue. But Gödel and a bunch of other people, how would I pick who to say? I mean, I don't know, Kleene, Henkin, Feverman, had showed that the analysis of formal proofs in a theory is not more certain than the actual content of the theory. You would think, okay, we're talking with this theory of infinite sets. You can't be sure of this stuff about infinite sets because they're infinite. How can we know them? But we can be sure about the strings of symbols. And this is a mistake. This turns out to be a mistake. Girdle shows, in effect, that the best reason to believe formal arithmetic or formal set theory are consistent in Hilbert's sense is that you believe they're actually true. The best reason to believe that no correct proof in PA ends with 0 equals 1 is that you believe PA is true. Or you could weasel and say, I only believe it's consistent. Well, Kreisler talks about that. We cannot prove consistency of PA from any assumptions more plausible in the first place than consistency of PA. Now, you can prove consistency of PA in many ways, and many of these ways are important for logical purposes. You can get real insights from different kinds of consistency proofs of PA. But I'm going to agree with Kreisel here that you cannot get new reasons to believe the conclusion from any of these proofs, because none of these proofs is more plausible than the conclusion was in the first place. And I mean, this is something that I take from Harvey's arguments. Why on earth would you believe that measurable cardinals are consistent? It's not because you have arcane beliefs about strings of symbols and set theory. It's because you think they make sense. They probably exist. I mean, that's fair, isn't it, Harvey? Yeah. We don't have more direct reason to believe that no proof in PA ends with 0 equals 1 than our own belief that PA is consistent, which basically comes down to our belief that it's all true. Hilbert was just wrong to think that we could gain security by stepping back to this realm of strings of symbols.
this could actually be made even more powerful if people could do the following. They could alter these systems in slight ways or write down string situations that are somewhat similar in which one doesn't know what one's talking about. They are inconsistent, but nobody can spot why without having the secret codes somewhere that somebody used that injected them. In other words, you can make this real. In other words, if you think you can look at ZFC plus a measure of cardinal and see that it's okay, what about this thing? You know, I think that would be an interesting game to play.
Yeah, actually, unfortunately, I was seeing as you were saying that, I get students who write down strings of symbols that don't make any sense, but I can tell they don't. But yeah, to do it in that focused way, yeah, that's, yeah.
Yeah, so I agree with Kreisel.
You were muted for the last part of that. Anyway, you agree with Kreisel.
I agree with Kreisel, and I agree with you agreeing with Kreisel.
Now, Gödel's original arguments were really hard to understand. I mean, psychologically, you look at the quality of people who worked really hard to make sense of this. They were really hard to understand. And honestly, maybe I'm making excuses, but I want to say that textbooks written in the 1950s were pretty hard to understand. It could be done, but the ideas are so new: arithmetization, diagonalization, recursive functions. For a while, when I would teach Gödel's theorem, we would come to arithmetization, and I would say to students, look, you in a sense already know this because you know that all the information on your computer is coded as zeros and ones. You know that things can be coded numerically. Actually, more and more of the students don't know that because they use such high-level graphic user interfaces. They're completely unaware of the computer language. But for a while, it was common. But in the 1930s, this was far from common. This was weird. And you will see textbooks going right into the 1960s saying, here's this difficult idea. We're going to represent sentences by numbers. And aspects of it are quite subtle and have to be done right. But the whole idea was just shocking at the time. There were so many generalizations to explore. Everyone competent who could engage with these from the start saw, oh, but you could also say, or you could also say. I mean, there were so many rabbits to chase. You didn't know which were the important ones. The basic results were so shocking. Actually, they were shocking in different ways to different people. There were plenty of people that Hilbert was refuting, who would say, oh, well, no science is complete. Of course, arithmetic's not complete. Nothing is complete. But they didn't mean a serious proof like Gödel gave, right? I mean, even to those people, it was shocking that you could give a hard proof of this. Bertrand Russell probably never got over his shock. He probably never grasped these theorems. It's hard to say. I mean, a lot of good historical work has gone into that. But he probably for the rest of his life believed it was just some paradox. That Gödel had come up with a paradox, and if you would think clearly, it would go away. But for other people, to people who pursued it productively, the results, even well understood, were shocking. So it was clearly a great result in logic. There's no question. Everybody knows that Girdle incompleteness is a great result. Question is, will it affect mathematics? Will it affect the mathematics that all mathematicians work with? And I think that's sort of what we mean when we talk about this project of concrete incompleteness. Are there incompletenesses of a sort that mathematicians would normally care about outside of logic? Now, of course, I had no idea which kind of audience I was writing for. Nearly all axiomatic theories in mathematics are incomplete. There's some sentence in the theory, T doesn't prove the sentence, doesn't prove its negation. This happens all the time. The group axioms apply to many different groups. The group axioms don't imply that there's 5 elements. They don't imply that there are not 5 elements. Well, this is deliberate. This is not what we mean by incompleteness. The ring axioms apply to many different rings. Again, this is deliberate, is not what we mean by incompleteness. An interesting example is for 2,000 years, people wondered whether the parallel postulate could be proved from the other axioms of Euclidean plane geometry. Now that's interesting on a whole lot of levels. And the answer now clearly no. The other axioms can be extended two different ways. You can give Euclidean geometry for every line and point that's not on that line. There's exactly one line through the point that never meets the first line. The Euclidean parallel postulate, that's not the form in Euclid, but it's been well known for 200 years that it's equivalent. Hyperbolic geometry, where you just negate the Euclidean parallel postulate. Some people will know that this is Tarski's approach. In Tarski's approach, you take one car of axioms. If you add the parallel postulate, you get Euclid. If you add its negation, you get hyperbolic. But you know, historically, this was also sort of true. Euclid himself already gives a proof that would rule out what we call spherical geometry. That's already in Euclid. Euclid himself sees only two possibilities: the parallel postulate and not having the parallel postulate, which we would now call hyperbolic geometry. We know that he could imagine this because Aristotle says several times various things you couldn't prove if you didn't make the assumption about parallels. Now, it's extremely unlikely that Aristotle thought there was another geometry that didn't have parallels, but he certainly saw that there were things you couldn't prove if you didn't use the assumption on parallels. He said so. Spherical projective geometry requires further changes, and the mathematicians who pursued this have known that for 400 years, that if you were going to do anything like changing Euclid to make lines always meet each other, you're going to have to change other axioms too. So the axioms omitting the parallel postulate, they're incomplete, but again, it's not what we mean by incompleteness. And there's an important reason why this is not at all what we mean by incompleteness, because the interesting thing is Euclidean and hyperbolic geometry interpret each other. From a modern point of view, they're not different subjects. They're different views of the subject. They're different geometries, but they are bi-interpretable. They're not different subjects, just different ways of organizing it. Using Tarski's axioms, each of them is bi-interpretable with the theory of real closed fields, the algebraic theory of real closed fields. So this is not two different subjects or three different subjects. These are just different ways of geometrizing the same algebra. The different ways of thinking about the same mathematical material. And that's part of the beauty of Tarski's axioms, is that this difference appears so concisely. I will say it's very hard to use Tarski's axioms to prove your favorite theorems of geometry, but they're absolutely the right axioms for meta-theoretic study. Now, Friedman has specified the incompleteness we're talking about, put this very well. The incompleteness phenomena in the modern sense of the term relates to formal systems surrounding those strictly mathematical concepts that are currently viewed as the basic notions from which all others are defined. This is for things that are somehow foundational. I would say for things that people might be surprised they're not complete. As I say, I think Bertrand Russell probably never really believed that his axioms for arithmetic weren't complete, that they left genuine arithmetic equations undecided. He probably never believed that. But as Friedman goes on, thus the focus has been on formal systems for natural numbers and for sets, and also for restricted concepts of set. And that's actually in a published essay, not just online. And I want to say this is one of the things that just immediately caught my attention when I started looking at this: interpreting arithmetic as a set theory. It's a chapter in Hayek and Pudlek, right? Arithmetic as set theory. Each finite set of numbers is itself a larger number from this point of view. So the set theory we get, you can describe it as the FC minus the axiom of infinity. Peano Arithmetic is that set theory up to interpretation. And the lesson I want to learn is that talking about up to interpretation is the right way to talk about theories for most purposes. Of course, you want to know what's an interpretation, but intuitively, what a theory means is invariant up to interpretation. So Friedman has done the most on this, and he states the problem of Gödel incompleteness theorems very sharply. We can view Gödel's first incompleteness theorem as an existence theorem only. We can say it's just an existence theorem, or we can view it as proving the independence of an arithmetization of the liar's paradox, which is probably what Bertrand Russell thought it was, but not with any deep understanding. He just thought that was the reason it didn't matter. In either case, one cannot view it as providing an intelligible instance of mathematical incompleteness. Now, it's extremely important to recognize the force of those statements. I'm going to say that I want to say that these are maybe giving too much away, but it's posing the question very, very sharply and correctly. When he says we can view Gödel's first incompleteness theorem as an existence theorem only, would I take that to mean for any axiomatic theory which contains enough arithmetic, there is this sentence, we can call it the Gödel sentence, the theory doesn't imply it and the theory doesn't refute it. It's certainly, this is true. This is certainly true, and it's certainly proved by Girdle. It's also true that if you saw this sentence written out as arithmetic, you could not read it at all. You could only begin to parse it by breaking it into many, many small parts, and that's what Harvey just brought up. Is we could try to find an exercise here where these sentences are readable but difficult of comprehension, and see what we can say about sentences like that. If you saw this written out as arithmetic, you would have no idea what it means unless you saw how it was created. I'm not the first to say that. I have no idea who was the first to say that. I think people have been saying that ever since they talked about this subject. Every step is correct. But I will agree that the Gödel theorem in that sense is not itself intelligible. You can't understand that Gödel sentence. You can understand how it was constructed, and you can say the construction worked, but you can't understand it by reading it. Or we can view Gödel's first incompleteness theorem as proving the independence of an arithmetization of the liar's paradox. Yes, you can. And it's been popularized that way a lot. And I don't just mean by commercial popularizers. I mean, lots of good mathematicians have introduced it this way. We can regard the Gödel sentence as a number theoretic statement, really a Diophantine equation. Well, the fact that it has no solutions means that it means there's no proof of this statement in the theory. We can view it as the Gödel sentence as a sentence that says there is no proof of me. Now, innumerable people have glossed it that way. This is surprisingly hard to justify technically. It's very easy to justify it as motivation, but it's hard to justify it technically. And this is a lot of what apparently got Fermat working on his 1960 paper on what is it, metamathematics in a general context, I think. It's really hard to justify the claim that that's what the sentence is saying. And at any rate, it makes Gödel's first incompleteness theorem seem like some logical or philosophical puzzle rather than a mathematical fact. And I think that's exactly how Bertrand Russell understood it. It was just a puzzle. And I want to be clear, on either of these views, the theorem is correct and is correctly proven. And it's a huge achievement in logic. Has anybody, I don't know if anybody's ever denied that this is a huge achievement in logic. Certainly nobody who understands it would try to do that. What some people deny is it's going to affect the rest of mathematics. And the point here is that neither of these views gives a satisfactory mathematical meaning to the Gödel sentence. I want to agree with Harvey on that. I think I'm agreeing with you. Is that, I mean, yeah.
Yes, I just unmuted.
So there's actually a problem of meaning or intentionality, even for the first incompleteness theorem, though the problem is much more famous for the second incompleteness theorem, because you can't state the second incompleteness theorem without saying what the sentence means. It's about what the sentence means. First incompleteness theorem is not necessarily about what the sentence means, but to make it satisfying as mathematics, you'd want to know what it means. The second is about that, but there really is this problem with both. Okay, now, when you compare this with Hilbert's ideas developed over decades. Hilbert didn't just have one set of ideas, and there's been tremendous scholarship spent on developing Hilbert's ideas, and how they went from one time to another time. I think there is no one correct view of what Hilbert meant, because this is over a period of 40 years. But here are some aspects that I want to relate to current research. Hilbert's theory was going to include enough geometry to recognize the symbols and proofs. It was not going to be coded or arithmetized. He's clear over and over again that this proof theory will involve recognizing shapes. You're going to need to be able to recognize shapes. Bernays said similar things. Now, he didn't say that in contrast to coding or arithmetization, because he hadn't conceived of coding or arithmetization, but he does insist on it. This is going to be a theory about strings of recognizable shapes. And in that sense, a concrete theory, because these are strings that you can write on the blackboard. It would use only a concrete, intuitive, finite fragment of arithmetic. I mean, he knew the Peano axioms. He was not going to use all of the Peano axioms. He was going to use a concrete, intuitive, finite fragment of them. And I take that, I mean, this is pulling it towards the concrete. And I want to say that recent progress has lived up to that. Now, Girdle, for his own reasons, Girdle proves a stronger theorem by proving that even the whole of Peano arithmetic won't prove its own consistency. But for conceptual reasons, Hilbert was more interested in hoping that a tiny fragment of PA would prove the consistency of the whole. So Gödel is here completely blowing away Hilbert's hope for a proof, but he's bypassing Hilbert's concern for the concrete intuitive, because he can say, even with the whole rest of the formalism, you won't get a consistency proof. And Hilbert wanted one proof theory that would, in his words, guarantee the trustworthiness of the whole mathematical apparatus. Well, Gödel shows that's impossible. We have some people today who still want to say, well, somehow we can rescue a lot of Hilbert's program. Well, people do rescue parts of Hilbert's program. I'm claiming to rescue part of his program, the idea of concreteness. But there are even people who want to say, well, we can rescue the whole program if we just think about it the right way. Girdle showed you can't. Now, so Hilbert never made this work the way he planned it to. No, I don't have the next thing there. So here's a place where the modern theory departs from Hilbert. In the modern theory, we don't. Well, I guess that's what I have. Yeah, recent incompleteness. Really, it does offer concatenation of strings to replace some numerical codings. Now, this by itself doesn't change what has to be proved. It's not that talking about concatenation of strings of symbols is a magic wand that gets rid of the difficulties that were handled by numerical coding. But it does present them differently. It presents them more intuitively, and I want to say more concretely. This offers no single finitist basis. Not only is there not some one foundation for all of math, there's not one finitist basis for it either. We really need a lot of crucial, more or less weak fragments. In the context of Gödel's theorem, that's notably Robinson arithmetic, S12. I mean, I'm not going to explain these, but I really wanted to flank EFA with I sigma 0 and I sigma 1. I wanted to put it in the middle there to show where it sits. But that doesn't mean anything if you're not familiar with it. And again, it offers current theory offers no single mathematical apparatus, but a really surprisingly ordered hierarchy. It is really it has been surprising for decades, I know this because people have said so, that we have pretty much one hierarchy of consistency strengths of theories. Now, in principle, there are even large cardinal axioms that branch. Neither one of them implies the consistency of the other. But there's not a lot of that. There's really almost none of that. So it's a really surprisingly ordered hierarchy. And Friedman and Visser have these intriguing results showing that when you measure consistency strength in just the right way, which is not the only way you would want to measure it, but when you measure it in the right way for this result, and somehow the only distinction between sufficiently expressive theories is their consistency strength, up to interpretability. Of course, their vocabulary can differ completely, but up to interpretability, the only difference will be, this is not exactly true. There are exact theorems on it. They don't exactly do what I'm saying here, but they're in this direction. So here's Hilbert's insight in logic. I have to admit that for various reasons, I often think I'm not sure I like David Hilbert, but I think that's wrong. You should like David Hilbert anyway. You've got to like his ideas. He works on foundations of geometry, foundations of arithmetic in the 1890s, and we're lucky now to have fantastic editions of that so that you don't have to go to Göttingen and read handwritten notes. And the foundations of geometry, well, the published version is maybe the best. It's wonderful, but there are also unpublished versions that cover different topics. Henri Poincaré says of this, of the foundations of geometry, says, one could confide Hilbert's axioms to a reasoning machine, such as a logic piano of Jevons, and one would see all of geometry come out. That's no joke about the logic piano. This is a picture of the logic piano. This is an actual thing that Jevons hired a piano maker to build. It started out, it would display all the truth table row for 4 letters. In fact, it didn't have trues and falses. It didn't have T's and F's. It had the letter in uppercase or lowercase, uppercase for true, lowercase for false. But it would show, in effect, all the truth table rows for 4 letters. And then on these keys down at the bottom, this is 40 centimeters high. I say that as if I know what 40 centimeters is, but I don't really think in centimeters. But you have these piano keys down at the bottom. You enter simple Boolean compounds of P, Q, R, and S, and the machine closes the rows inconsistent with those compounds. So the machine, in the end, if you enter premises of an argument, in the end, the machine is displaying only the counterexamples to that argument. And if everything is shut down, it was a valid argument. Well, if the negated conclusion shuts everything down, then it was a valid argument. So this is sentential logic with 4 atomic sentences. This is, in fact, totally inadequate to Hilbert's geometry, and Poincaré knew that. Poincaré was not an idiot. Poincaré, he's saying it's as if. But it was as if that. Poincaré was right about Hilbert's intention. Hilbert maybe hadn't even seen it as clearly as Poincaré, because maybe he hadn't read as many of the Italians as Poincaré. But Poincaré saw that Hilbert was developing precise, mechanically explicit axioms for geometry. The proofs would fall out. The proofs would be correct or incorrect independently of what you think. It was going to be completely mechanical. Several people had actually related this to mechanical ideas at the time. Obviously, Jevons. Jevons went and hired a piano maker. As far as I know, Hilbert was not interested in machines, but he was interested in this kind of mechanical precision, even before he saw it so clearly himself. And I would tell you, we often hear that Poincaré opposed Hilbert's logic. Okay, here's one important key to reading Henri Poincaré. He likes to make jokes, and his jokes are generally a little superior. He likes to be smarter than other people. But he was not opposed to Hilbert's logic. He believed that lots of Hilbert's logic was terrific stuff. He was opposed to logicism as a comprehensive understanding of mathematics. He thought that was a disaster. But in this passage there, he was praising Hilbert. He was nominating him for the Lobachevsky Medal. He was nominating him for a very prestigious prize, which Hilbert got. I mean, of course, right, at this time, if Henri Poincaré recommends you for the medal, you're going to get the medal. But Poincaré regretted that only the logical side seems to interest Hilbert. They met a few times. There don't seem to have been any very revealing contacts between them. In fact, the first time they met was completely unrevealing. Hilbert, as a student, was sent to Paris by Felix Klein, along with Edward Study. They met Poincaré, and Hilbert said, well, no, I think it was Study that actually wrote the letter. Studi actually wrote the letter saying, Professor Poincaré seems to be very distracted most of the time. I'm not sure he really wanted to talk to us. But Hilbert came to see that for this formal logic to persuade the finitists, the meta language would have to be purely intuitive, finite, concrete. I'm stressing here that he is pushing the same question that we're pushing now in terms of concrete incompleteness. He wants to change the minds of actual mathematicians who are neglecting the new logic, and they shouldn't be neglecting the new logic. And he wants to do that by giving them a finite, concrete proof theory that they will see helps them to prove theorems. I will say not every great mathematician feels that way. Felix Klein was perfectly happy to build a program at Göttingen that would produce all the best mathematicians in the world. He didn't care if he changed everybody else's mind. He sent students off to Johns Hopkins. All right, Bob. Klein sends students off to Johns Hopkins to make Hopkins a good school, but he doesn't need to convince everybody of anything. Hilbert wants to convince everybody. And Hilbert believed that a lot of mathematics was already purely intuitive, finite, concrete. Number theory, geometry, not analysis. Hilbert has this wonderful book called Geometry in the Imagination. It's called Geometry in the Imagination in English. This is a terrible disaster. The German title plainly says intuitive geometry, anschauliche Geometry. It's intuitive geometry. It's not geometry in the imagination. And when you read the book, it's brilliant. He'll take some fairly deep geometric theorem, and he'll give you some elementary considerations that set it up. And then he'll say, at this point, to be correct, we would use analysis. And he skips that step. And then he says, but it would show us this, and he gives the rest of the elementary reasoning. He gives you the whole intuitive part of the proof. He notes that part of the proof uses infinitary mathematics, but he doesn't give that part, because we know that the finite results of infinitary mathematics are all correct as finite results. So if you want to see Hilbert explicitly telling you what is finite intuitive mathematics and which parts would need analysis, it's right there in that book. Numerous, hundreds of examples, a half a dozen really important examples. If you want to know what he means by intuitive. He tells us, consider the nature and methods of ordinary finite number theory. It can certainly be built through number constructions by means of contextual, intuitive considerations. This was not obvious to people. Lots of people thought that most of number theory used weird abstractions. You had to use this idea of group just to read Hecke's book. Well, of course, you have to use analysis to give Dirichlet's theorem that every arithmetic progression includes infinitely many primes. You used... Who knew what you were using to apply Dedekind-Weber's theory, Riemann theorem, to number theory? But he says, no, that at least ordinary finite number theory can certainly be built through number constructions by means of contextual intuitive considerations. And that's what he means by contextual intuitive in meta theory, when he wants his proof theory to be intuitive in this sense. And he tells us For Hilbert, the following is not a truly finite. This is his example, which he gives repeatedly. You can say for every number n, there's some greater prime. Every number n is less than some prime. Every number n has some prime greater than it. And this is the right way to state the infinitude of primes in elementary arithmetic. And Hilbert says that's not a finite statement because it's left you looking at all the natural numbers beyond n. You can't do that. I mean, you can do it formally, but that's not going to be finite and intuitive. To be finite intuitive, you need an upper bound, which is more or less read off of Euclid's original, the first published proof of the infinity of primes. Every number n is less than some prime that is in turn less than n factorial plus 1. You don't have to look at the whole infinity of natural numbers to find the next prime. You can just look up to n factorial plus 1. So this bounded statement is shorthand for a plainly finite statement. This is what Hilbert tells us. It means either n plus 1 is prime or n plus 2 is prime, or, and we're going to get up to n factorial plus 1. That's just a finite statement. Now, this has been bugging me more and more lately as a philosopher. Don't try to write that out for n equals 5. You can. It's humanly possible. Not humanly possible for n equals 100 to write it out. But you don't even want to write it out for 5, right? You really want to use the abbreviated form. But for Hilbert, these are intuitive finite statements. Now, a lot of people have worked hard to understand exactly what Hilbert meant by finite in this context. There's terrific work on this. There's analysis of his correspondence, of lecture notes, and it's very insightful. But I think finally, and some people want to argue, this is maybe the leading candidate is primitive recursive arithmetic, is what Hilbert meant by finite. That's probably the leading single candidate. But I think there's a general consensus that Hilbert never made a final decision. It's just not, it's not a question you can really answer for Hilbert across his career. He never made this decision. Crucially, though, he was explicit that statements with no quantifiers are finite and that they can have free variables. This is like what we mean by pi 1, except that it's not clear what he thinks about bounded quantifiers. So here we have Fermat's last theorem. Take any numbers, any integers, any integers a, b, and c. If none of them are 0 and n is greater than 2, then a to the n plus b to the n is not equal to c to the n, right? No quantifiers. We said at the first, take any numbers, but there's no quantifier in the statement. And Hilbert says this is finite because every individual case can be verified by routine calculation. Again, do not try these calculations for n greater than about 1 million, even on a computer. I think 1 million, I don't know, I'm not a computer scientist. There's some fairly easy to name number where nobody can do it right now. And it's also, so besides the crucial restriction to a finite fragment, it's also crucial, Hilbert was clear that the formal, explicit, not finitary apparatus of mathematics must be consistent. Now, all thinkers from the dawn of time, unless they were great paradoxers like Nietzsche, have thought it's good to be consistent. But Hilbert means something specific here. Hilbert is making a specific claim. And he tells us in 1900, in investigating the foundations of the science, we must set up a system of axioms, but above all, I wish to designate the following as the most important among the numerous questions which can be asked with regard to the axioms to prove that they are not contradictory. Like I say, there's almost nobody hasn't thought that's a good thing, but people didn't pursue it as clearly as Hilbert. Now, this raises a question that I want to say is not merely philosophical. Could set theory or even Peano arithmetic really be inconsistent? Is that even thinkable that they're inconsistent? And for Hilbert, absolutely it's thinkable. And the reason it's thinkable is that these are precise formal theories. They are not intuitive statements, and so our intuitive sense of them is not enough. We have to check that the precise formal statement was precisely and formally correct. We need a finite concrete proof theory to verify that our theory of infinitary mathematics is consistent. He sees there will be no proof that there really are infinite sets. He believes it, but you're not going to prove it. But you can prove that the theory of infinite sets does not contradict itself. Well, today, since Girdle, we say, yeah, you can, but only from assumptions. Hilbert thought you could just do it. Hilbert thought you could just do it and be done. Hilbert believed that all finite sentences of arithmetic, in his sense of finite, have finite concrete proofs. And this was his model for finite concrete proof theory. Those proofs will be finite and concrete in the same way. Gödel shows that modulo Hilbert's vagueness on what is finite, this is just wrong. It's just not true. The statement, if P is a proof in Peano arithmetic, then P does not end with 0 equals 1. He says, this should count as really finite in Hilbert's sense. Now, Hilbert's sense was not perfectly precise, but this should count as really finite. And in particular, Gödel is saying, I can turn that into a Diophantine equation. And surely that's finite in Hilbert's sense. And so this, but it can't be proved using all of Peano arithmetic. It does not have, in that sense, it does not have a finite concrete proof. Now, Gödel politely pointed out that this does not entirely prove Hilbert was wrong, because Hilbert hadn't been perfectly clear what he meant by finite means of proof. And one important outcome of that was the Gensen proof, which, I mean, there are important proofs of consistency of PA, but practically, this did show Hilbert was wrong. They don't start from more secure assumptions than the assumption of Peano, or the consistency of Peano arithmetic. They're really important proofs in a technical sense. They are not more persuasive than your belief that PA looks consistent. On reflection. But here's the thing to say for Hilbert. Truth comes more quickly from error than from confusion. Hilbert was wrong. He focused a lot of attention on a specifically mistaken claim, and he got a lot of other people to pay attention to that specific mistaken claim, and truth came more quickly from that clear and important mistake than it ever was going to come from confusion about, gee, what does consistency mean anyway? This statement is first given to us by Francis Bacon there in 1620. See, I just wanted to show you a picture of him. Gödel's two incompleteness theorems appeared in 1931, though the second wasn't published. You have decades of rapid development, and I want to emphasize these were continuous chains of results building on each other. These were not just separate new ideas. The reason I want to stress that is to tell you, I have no grasp of that continuity at all. I mean, this is a huge intellectual development, and I have not immersed myself in its history, but I've studied enough of its history to know, yes, this is one organic development. Everybody is using everybody's results. Everybody's aware of everybody's results. I will mention Pfefferman's Arithmetization of Metamathematics in a General Setting, 1960. This was particularly important for the work I'm going to discuss. I mean, it stood out on its own already at the moment, but also it stands out in relation to my project compared to lots of other stuff that's also important, but it's not my project in this paper. Now, there are a lot of directions of current work. Harvey has just this fall posted, okay, swift reformulations of Gödel's second incompleteness theorem in terms of recursion theory. I take it this came out of thinking about what you said, for example, in your Wuhan talk, but it's not in the Wuhan talk, right? I mean, the posted results are subsequent to that, but immediately subsequent.
Yeah, I went through some evolutions when I started to write for the conference, and it stabilized. It stabilized for several months and I'm going to take an excerpt of it and show it here after your talk.
Okay, yeah. All I could say about that is to summarize the webpage. I'm not going to talk about that. I mean, it's online, and he's going to show us some of it in a little bit. Nor will I talk about currently known cases of concrete incompleteness. This Ramsey theory, Boolean relation theory, Harrington's principle. I have no new angle on those, and you can see them. Harvey's work, Young Chung. You can read Young Chung's work. I'm going to focus on what Visser calls coordinate-free versions of consistency and compare this to Hilbert's goal of concrete, intuitive, finite proof theory. Now, just like all the earlier work on Gödel's theorem, Visser's is not a separate development, but I mean, I'm going to talk about his papers. Visser, building on Pudlak, building on Friedman, states the goal approximately this way. We may rephrase the second incompleteness theorem as no recursively enumerable theory T interprets Q plus con T, where con T is a sentence expressing the consistency of T. Now, I would confidently expect that if you have not been looking at these papers, you don't feel what that means. I mean, for a while, I didn't feel what that meant. And I'll tell you, I'm actually a little bit puzzled as I work on all this new stuff, and I think, should I change my Gödel's theorem course this way? Because in light of this, we don't do the second theorem. I just proved the first theorem. And I'm not sure I'm going to change my undergraduate introduction to Gödel's theorem because of these new results, but it certainly changed my view of the subject. So what is Q? What is this Robinson's arithmetic Q? It's a theory of arithmetic so weak that it introduces no serious logical content itself, somewhat like Hilbert's goal for purely intuitive, finite, concrete meta theory. I'll say more, but what is interpretation? Well, there's a whole lot you could say about that, but what I want to call attention to, it's an agile tool for comparing theories, and in this context, precisely for making concrete sense of technicalities. Sometimes abbreviating the technicalities, sometimes getting rid of them, but always at least presenting them in more concrete terms, because you wouldn't do it otherwise. How is consistency expressed? This is the point of Visser's paper on coordinate-free formulations, and he tells us it has no fully satisfactory answer yet. He discusses the reasons for that. I'm going to be very clear. This work, Friedman, Visser, Yongchang, and others, it's going on now. It's not finished. And that's part of why I don't know how I would bring it into my course, but I'll keep thinking. Okay, so what is Q? By name, it's Robinson arithmetic. No time here for the whole history or even the axioms. I can't even give you the axioms of it. It's arithmetic with nearly no induction. It gives the basic definitions of plus times. It gives the simplest facts on successor. The upshot is it proves all specific equations of arithmetic, like 5 plus 7 equals 7 plus 5. It proves that. It proves every equation you can write in arithmetic without variables, just names of natural numbers. If it's a correct equation, it proves it.
It does have an existential.
It
does have an existential axiom that
yeah,
not zero, then it has a predecessor.
Yeah, and people say, and correctly so, that's a very weak form of induction. Every number is either 0 or else a successor of something. And from the other axioms, it can't be both. So it proves all the specific equations, and here's where Harvey's remark is relevant. It can work with generalizations, and it can prove explicitly bounded parts of them, but they do have to be explicitly bounded parts. I mean, this is where you use that existential. So you take any bound, say 34,000, I don't care what it is, whatever it is, an explicit bound. We can prove that for every x and every y less than that, x plus y equals y plus x. We can prove any explicitly bounded part of commutativity of arithmetic. We cannot prove commutativity of arithmetic.
But that proof of the proof of that thing is quite long in Q.
It's quite long, you say?
Yeah. A lot of steps.
Oh yeah. 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 Well, you have to spell out the 34,000, even the statement of it. The statement of the form you've read has 34,000 clauses. So
well, now you can beat that because you have plus and time. So you can, you see, it's not that long. It's about log that, you know, it's log that. It's not bad. Yeah. But then you got to prove this, you see. So I don't know that the proof theory, I don't know that the proof theory of Q has been directed to this kind of thing. It might be pretty interesting.
Yeah, and I think there's one reason why it might not have been is that S12 already does this kind of thing.
There's a length of proof subject here, I see.
Yeah. Well, that's a remark of yours that I take very seriously, but have not explored. We've got very serious, useful theorems in arithmetic that are complete. They escape the Gödel phenomenon. Real closed fields, the most famous example. But when you start trying to do anything with them straight from the theory, you run into length of computation problems, which are very like the consistency problems. So I just haven't explored that myself. So Q can do this. What we need to know is Q can prove the Gödel incompleteness theorems. You can state them as theorems on Q. Every consistent recursive extension of Q is incomplete. Every consistent recursive extension of Q is incapable of proving its consistency statement, depending on what you mean by consistency statement. Which shows you that those theorems, and I just realized this while I was writing this slide. I mean, that shows you these theorems really are calculational. As I was writing this slide, it made me better appreciate the concreteness of the theorems. They're about calculations. And what we need to know is this is a general attitude, but I think a correct one. When Q plus some other assumption proves some general fact, then Q supplies the meanings of the arithmetic operations, but the generality really comes from the other fact. If you can prove a generalization in an extension of Q, that came from the extension, not from Q. So when we say that T does not interpret Q plus con T, this doesn't just mean that the theory T can't prove itself consistent. It means that T cannot express any way that T could be consistent with the specific calculational mathematics in Q. Not only does it not prove it is consistent, it can't even express a way it could be consistent. Now we believe, hold on, gotta plug in my computer. There you go. We believe PA is consistent, but PA can't prove it. And furthermore, this is a new insight from these new ways of stating it, going back to Black and Friedman. PA can't even express any specific way it could be consistent. What is interpretation? Well, again, I'm writing this for students because students should pursue this. This won't be news to the people whose faces I see right now, but to interpret a theory S, which includes certain axioms in theory T, means to translate the vocabulary of S into the vocabulary of T in such a way that axioms of S are translated into theorems of T. I don't care if they're axioms of T anyway, they're things T can prove. The most famous interpretation in the history of mathematics is where you interpret the axioms of Euclidean plane geometry, which deal with points and lines, in the language of algebra. Each point is expressed by a pair of real numbers. The distance becomes an algebraic expression. And what you show, once you've given all the apparatus, is that Euclid's axioms translate into theorems of real number algebra. So Euclid's theorems automatically also the theorems of real number algebra. Hilbert one of Hilbert's main motivations for at least some editions of his lectures on foundations of geometry was to give precise versions of the interinterpretation of geometry and algebra, to make this really precise, exactly which parts of geometry are bi-interpretable with which parts of algebra. And the best known precise version today is Tarski's axioms. This is first order. Hilbert was not always first order. They make both Euclidean and hyperbolic geometry, first order theories of them, bi-interpretable with the first order theory of real closed fields in algebra. It is very pretty stuff. Intuitively, these are three ways to think about the same mathematical material. Anyway, I will tell you that once I figured out how you show this, and once I figured out how you work with coordinate hyperbolic geometry, which is not something I learned in grad school, they're just three ways to think about the same material, three beautifully different ways, but they're the same material. In this case, it's often easier to give proofs from the algebra than on the geometric side, very often easier to see the geometric side. To put it into the context of incompleteness, I've got this beautiful quote from Visser: "A basic insight concerning interpretability is the Gödel, Hilbert, Bernays, Long, Henkin, Pfefferman theorem." We can't put the history of every theorem into every theorem's name, but Albert tries to do it right here. And he knows he's leaving some people out, but Henkin simplified and clarified Gödel's completeness theorem so it shows not only that every consistent first order theory, well, countable, has a countable model, but that it has a model where it's talking about the very expressions that occur in that theory. The elements of the model are equivalence classes of terms in the theory. The extension of any predicate is the set of all terms that the theory, well, actually a suitable chosen completion of the theory, proves have that property in the theory. You build the model out of the statements, out of the vocabulary and the theorems of the theory. And what Pfefferman shows, building on work by Girdle, Hilbert, Bernays, Long, I don't know who all, I'm just taking the list that Albert gave. He shows that inside of arithmetic, you can interpret any consistent theory as a true description of a structure built from the terms and theorems of that theory. And this will not work for an inconsistent theory. And so we can define the consistency statement con T over the base theory Q of Robinson arithmetic as the weakest statement, such that using Q and con T, you can build a Henkin-Pfefferman interpretation of T, and thus the interpretability version of the second theorem, and that what the content of the second incompleteness theorem is. Conversely, then you cannot interpret Q plus con T in T if T was recursively axiomatized. Of course, Pfefferman gives a really pretty example where you got something that's delta 2 and can interpret its own inconsistency. But overall, I mean, here's the philosophic conclusion, and the reason I didn't say I had to change the title of my talk. Overall, this kind of research leads us away from arithmetization, away from regarding consistency as an unreadable Diophantine equation. And I mean, it's important that Diophantine equations are not nonsense, but this one's awful hard to read. But this leads us away from that towards reading it as a theorem about what theories say and the strings of symbols they use to say it. And I entirely agree with Visser saying the arithmetization-free version is closer to an honest mathematical theorem. I mean, we're making the thing more like regular mathematics all the time. And it takes decades, and it needs to take decades. It's not because people haven't been making progress, working and making progress, but there's a lot yet to do. Okay, for more on this, read Visser, which will require reading Friedman and lots of other people. What problems remain on this approach? Well, I will quote Visser just to show the scale of this. Now, some of you will know exactly what he's saying, and others just appreciate it. Our solution is, in a sense, not quite satisfactory, because this equivalence relation we need is EA provable equivalence, where one would like something like S12 provable equivalence. Also in the case of consistency, as opposed to cut-free consistency, we only have this is a lot of technicalities, correct technicalities, not impossible technicalities, but technicalities, right? If I'm going over and talking to a friend of mine who does Brownian motion on manifolds, they don't want to hear this. This is not natural to them. So these are serious problems, but I want to say they seem workable, not hopeless. And in fact, progress has been steady on these things. And partly we have this theorem that just amazes me. You'd like to say that if one theorem, that a theorem is interpretable in another, just in case consistency of the second implies consistency of the first. That's not true. That's not true, but something like it is true. A theory is B is interpretable in A if and only if elementary function of arithmetic proves that cut-free consistency of A implies cut-free consistency of B. Yeah, I'm not going to explain those technicalities. They are technicalities, but it's still, it's a shocking piece of progress in understanding the relations between these ideas.
Do you want to say who actually proved that?
No, because Albert says there was some third party involved, but Harvey was on that. Yeah.
That's a theorem of mine.
Okay, that one's, yeah. Okay, yeah, right. It starts with Wilkie. Is it Wilkie in Paris? To prove a much weaker version, just for pi 1 sentences.
I don't know where the third parties come in, but I think I think that's literally from a paper of mine.
Okay, yeah. In this sweeping version, the best version of it I found anywhere else was only for pi 1 sentences, not axiomatized theories. Yeah, so I'm perfectly willing to believe this is entirely you. Yeah.
Yeah.
I do want to talk about the philosophic question: could arithmetic possibly be inconsistent? Because this is I'm talking in a philosophy department, right? I mean, I'm teaching in one, I think. Young, you're in a philosophy department, right? Well, we should.
Can you repeat?
Yeah, I mean, well, I'm talking in a philosophy department, right? So I'm allowed to ask philosophical questions.
Yeah. You have time to talk about this, please. Yeah.
What? Say again?
Yeah, you have time to talk about this part. I think it's especially about consistency of PA. Yeah.
I mean, Poincaré and Hilbert and lots of other people knew this question only arises for formalized arithmetic. We have the practical consistency of counting and bookkeeping is well tested. People count and add and subtract and multiply all the time, and they don't get it wrong very often, although they do sometimes. This is really, really well tested. But when we're talking about formal arithmetic, what it comes down to, Peano arithmetic. We're talking Peano arithmetic, it comes down to the axiom scheme of induction. You take any formula, phi of x, in the language of Peano arithmetic. Here's an axiom. If phi of 0, and for every x, phi of x implies phi of successor x, then for every x, phi x. It's a lovely theorem. Dedekind already knew this in a stronger version because he wasn't talking about first order formulas. He was talking about all sets, which he had an ability to do and we've since lost. So there's infinitely many axioms for every formula in the language of Peano arithmetic. We believe this. Now, it's a bold claim to say that you grasp the expressive power of general formulas in the language of arithmetic. We have virtually no experience of anything with more than 3 quantifier changes and anything less, I don't know. I mean, we use abbreviations of things that are thousands of characters long, but we still don't use arbitrarily long formulas. So it's a bold claim to say you can look at that and say, oh, I know that's okay. I know that's okay. Now we do claim to know it's okay. I claim to know it's okay. I'm not really concerned that Peano arithmetic is going to be inconsistent. I'll tell you, when Nelson announced his proof of an inconsistency, I just felt terrible. I thought And without he couldn't be right, and I was not happy about that.
Of course,
But the fact that,
you know that it's important. It's important to realize that all of that, every instance of that follows from one simple instance with sets in it. In other words,
yeah,
go beyond. If you go beyond pure arithmetic, if you buy into a tiny amount of sets, then it becomes, then you just need one instance and everything follows.
yeah. But then you've got your set theory. Now it's going to have, if you're using Zermelo and Frankel, it's got an axiom scheme. And then if you want to pass to Gödel Bernays, now you're back in the finite, but now you've got classes on top of
But
sets.
you want to use ACA not or ACA, ACA not, or ACA not a little bit more than ACA not. In other words, you can minimize this. In fact, I don't know if anybody's really studied how simple you can get a single instance of induction that gives all these. How simple you can get it with a certain, if you go with a microscope in there.
Yeah. But still, whatever foundation you fix on, when you're proving theorems that need this, you're going to need cases of it. And that's what we really have experience of, is cases of it. And throughout history, of course, we've only seen 0% of the cases. That is only finitely many. And
on the other side, one has seen higher order concepts used in inductions that are even more complicated than the one that's enough to give these. So you can argue that we do have experience, that we do have experience with enough induction that you can't just argue that on simplicity. I agree on arithmetic induction, we don't. But if you allow more general induction, even at a fairly innocent level of a little bit of set theory, then you, nothing like iterative set theory, just sets of integers. Then we do have experience with a lot of those.
Yes.
In the sense
but here's where I think a point by John Maybury is relevant. John Maybury makes another point. We've only done induction for conditions that make sense. We don't have machines cranking out consequences of the induction axiom for formulas that nobody knows what they mean. We only do it for conditions that make sense. And if the formalism does conceal an inconsistency, we would expect that to lie in the cases that have no apparent sense. And in fact, they can't make perfect sense because they lead to contradiction.
But you'll have to square that. This is an interesting comment, but you'll have to square that with the fact that I can write one down that makes very good sense that's a little higher order, and it formally implies the ones that don't make any sense.
Well, I mean, John's not with us anymore, but I mean, I think the direction this is going is to show that those others are cases. Well, we haven't done that with lots of things that are nearly cases that aren't because they're just stated wrong. And we don't have a lot of experience with those.
I'm talking about something formal. I'm saying that every instance of induction in PA, including the ones with nonsensical induction hypotheses, is formally follows from one sensible induction that's a little higher up. Formally follows.
Yeah, but of course, I mean, if PA is inconsistent, then they all follow from everything.
The point is that we believe in the induction, even if it's beyond arithmetic.
Yeah, sure.
I'm saying one sensible induction beyond arithmetic implies all the nonsensical inductions inside arithmetic.
But then you're committed to induction outside arithmetic, and that has its own problems too.
Yeah, but you can't say that it doesn't happen in mathematics.
No,
it's happening in mathematics.
Yeah.
All right.
But I actually want to give two good reasons to pay attention to this that don't contradict what you're saying. The first is, this actually shows that Gödel's theorems should increase our confidence in the consistency of Peano arithmetic. You know, when you read popularizations, the first step, they say, oh, mathematics can't prove it's consistent. Gee, so we should be worried maybe it's not consistent because mathematics can't prove it's consistent. And then these same popularizers go on to make the correct point. Well, look, if it did prove it was consistent, that shouldn't convince you, right? Because every inconsistent theory does prove it's consistent. And then they say, well, so this just doesn't move the ball on consistency. And that's wrong. It does advance our knowledge of consistency precisely because Gödel's theorems put lots of cases of induction to the test that we never did before, that no other context would have done. Gödel's theorems actually should increase our confidence. I'll come back to that. But the other thing is, it also lets us see that Nelson's non-standard analysis is what arithmetic would become if PA with full induction was found to be inconsistent. It won't be found to be inconsistent. I just said I was made very sad when he announced an inconsistency proof. It's not going to happen. But you can see this counterfactual. His non-standard analysis is what arithmetic would be if PA was inconsistent. Now I'll expand that. Okay, Girdle has shown that if you can prove con PA in PA, then you have proved PA is inconsistent. Today, there are many known ways to prove something like con PA in PA. And as Harvey is bringing up, there are many known ways to prove exactly con PA in something that isn't just PA. And if you could extend one of those or narrow one of them to a proof of con PA in PA, you would become famous. You would become so famous they wouldn't even give you a Fields Medal because you wouldn't want it. You wouldn't need it. Do not try to do this. It's not going to happen. You'd be wasting your time. But the point is that Girdle has shown tests for consistency that nobody could have imagined before and that PA passes. So yeah, consistency of PA has passed much more rigorous tests like this using Gödel's theorem than anyone could have imagined before those theorems. So the Gödel's incompleteness theorems really should strike you as a powerful test of the consistency of PA and a test that it passes. Not a proof, but a test. And as this claim that Nelson's non-standard analysis is what arithmetic would be if PA is inconsistent, I mean, I owe this also to John Mayberry. There's a plausible claim. I'm not sure if this has been proven or not. I wouldn't be at all surprised. If PA turned out to be inconsistent, then there could not be any maximally strong consistent subtheory. Well, it's a counterfactual. PA is not inconsistent, but I will take it that if it were inconsistent, we still know there's no maximally strong consistent subtheory, which means that there are infinite chains of ever stronger consistent subtheories, and each of these looks like Nelson's non-standard analysis to the next one. Each of these is a model of part of PA, but less induction than the next one. Each of these allows numbers that don't satisfy the stronger induction axiom in the next, so those numbers are infinite according to the next. And so you can interpret fractions, which are infinitesimal according to the next. I don't know if Nelson ever thought that his non-standard analysis was a patch in case PA was inconsistent. Whether he thought that, I have no idea, but it is one. Non-standard analysis is a very good guess at what mathematics would look like if PA was inconsistent. If PA isn't inconsistent, but here's that. And I do also, okay, I won't worry about that. So maybe we can move to discussion.
Excuse me, have you finished?
Well, I will mention in terms of concreteness, when we want to get results that strike mainstream mathematicians as important, remember that lots of important mainstream mathematics is not really very accessible to most mathematicians. it's known to be important, but it's not really terribly accessible. Hilbert's Theorem 90, extremely important in number theory, has precisely one accessible consequence. Mathematicians don't learn Theorem 90. They've heard of Theorem 90. They know that you can still win a Fields Medal for improving Theorem 90. They don't understand Theorem 90. So it's not just logic, where lots of mathematicians don't get the stuff. Anyway, so now I'm finished, yes. Okay.
Young, should I hit share screen now or not?
Oh, I need to stop sharing. Yay.
Okay, you have to stop share. So I'm going to hit share. See, no, wait, I'm going to hit share screen. Here we are. Okay, is that a work?
Yes. Yeah.
Okay. Yeah, this is quite short. I didn't want to, I'm not going to give a lecture here. I just want to point out there's two references I want to mention that might clarify some of the things you talked about that I was doing. Okay. So the first one is called this, and it's what came out of the Wuhan conference on Gödel's incompleteness. There we were talking about. That's the first one I want to mention, and then there's this one down here. This is an FOM posting I just made. So I want to talk about these two manuscripts, what's in here. I didn't want to put really anything too explicit about this, but basically I came up with this particular kind of syntax-free version of Gödel's second theorem. That no consistent extension of PA, infinitely axiomatized, finally axiomatized, infinite language, finite language, I don't care. No consistent extension of PA is interpretable in any of its arithmetic theorems. Okay. No inconsistent extension of PA is interpretable in any of its arithmetic theorems. And what I do is I show that this statement here is equivalent to Gödel's second theorem for extensions of PA, equivalent to Gödel's second theorem for extensions of PA, where the equivalence with Gödel's second theorem is done without getting involved in any aspects of the proof of Gödel's second theorem. In other words, you don't know anything about how G2 is proved, you don't want to get involved, but you can show softly, relatively softly, that this thing here is equivalent to G2. So that's why I call it a no interpretation form. I call it a no interpretation form. I mean, it's even more specifically has properties beyond being coordinate free. All right, so what accompanies this is also a characterization of the consistency statement. Now, this thing has nothing to do with the consistency statement. But along with this work is a characterization of the formal consistency statement as the weakest statement which can be used to interpret. And then Visser took that and is running a mile a second with it. I haven't even kept up with him at all. and called it Friedman reflexivity, and has done a lot of things with it. I asked Visser, what are you going to do? Do you want to do something with, there's another theorem in this paper, and this is proved, by the way, you'll find a proof of this in here. It's actually proved there. A proof of the equivalence with G2, in fact. The other thing is that, what was I going to say about this? Yes, for PRA, for primitive recursive arithmetic instead of PA, no consistent extension of primitive recursive arithmetic is interpretable in any of its pi01 theorems. I show that's equivalent to G2 for extensions of PRA. That's equivalent to G2 for extensions of PRA. And Visser says, and also con of a theory in that context, just extension of PRA and recursively axiomatized and so forth and all that. The con statement is also the weakest thing that does the interpretation. So Albert said he can run a mile a second with that too in somewhat different directions. And he's so busy running a mile a second with this that he hasn't gotten to it. So I have to catch up with Visser. He's fast. All right, so that's what is most relevant to the discussion about G2 here. Now, having said this, I believe there's such a thing as the intended G2. Gödel intended G2 to be completely syntactic, having to do with the obvious consistency statement you get by thinking about what he wanted to think about. And that, of course, will lead to a development, if you take that seriously, that's quite different than this here. Quite different than this here. And that needs to be fleshed out a lot. And I've been talking, about that in some private conversations. Okay, so we've got this no syntax at all, and then we've got pure syntax form, neither of which I think had actually been mined out fully. I mean, but we're starting to mine these out. It's interesting that the theorem is so great of Gödel's that it's taken almost 100 years to figure out how the right ways to say it. And they're totally different ways to say it that are very important in their own right, almost 100 years later. I mean, that's pretty sexy, I think. All right. Now, this paper also states the state-of-the-art tangible incompleteness. And I want to mention this because you've alluded to how this incompleteness might touch real math. So I have a little summary here. I'm certainly not going to talk at length about this, but every order invariant relation of a certain kind. So order invariance is an extremely strong condition. It means that there are only finitely many order invariant things in a given dimension. I mean, there are only finitely many things. The most concrete things are, among the most concrete things there are in mathematics. Okay, so every order invariant relation of a certain kind in rational vector spaces. In rational vectors, not vectors. In other words, vectors of rationals. Has a maximal square. Well, if it has a maximal square, that's just the most basic form of maximal principle used all through mathematics, which is a special case of Zorn's lemma. But I'm in a countable context, so maximal objects are easy to come by. You just enumerate and go through everything. So I discovered that if you look at order invariant relations of a very specific kind, then they always have maximal squares. Is trivial. That's an undergraduate exercise. But they always have a maximal square, A cross A. So it's a binary relation R. A cross A contains an R. They all have a maximal square with retaining some order invariance, whereas they're order invariant with respect to integers higher up than the section, than the placement of the section. A section means you just fix a coordinate. You fix coordinates. Sections of a higher dimensional object, you fix finally many of the coordinates to be particular numbers, particular rationals, and then you look at the set you get from that. It's called a section, which is fairly standard notation. And so all the sections are ordered invariant, not everywhere, but over the integers higher up. So we start with an order invariant relation. We go to a maximal square and we lose some order invariance, but retain a limited amount of order invariance. You can do this, but you must use large cardinals. That's the theorem. So this is getting pretty close to some very well known mathematics, doing a maximal square in a relation, taking sections and having order invariance with respect to the integers. This is pretty sensible, Colin, wouldn't you agree? And I'm saying that this requires large cardinals, and it's equivalent to the consistency of large cardinals. Now I had another, let me end with this. I have a posting on the FOM, number 918. And this one is called Tangible Incompleteness and Clique Construction. So up here, you know, this is all infinite. This is all countably infinite up here. I mean, it's seriously countably infinite because I'm talking about a maximal object. You know, maximal. It's countable, but the maximal object, you know, could be a pretty complicated thing, right? But infinite. All right, over here, I wanted to make everything finite. Now, everybody's familiar with how you build a clique in a graph. You can build a sort of a maximal clique by doing greedy algorithms. Put it in if it's still okay, and forget about it if it's bad. Okay. But you can also there's a non-deterministic form of that, which says that if it's bad, that if it's okay to take it, it might be poisonous. So if it's okay to take it, you can, instead of taking it, you can take something else that bans it. In other words, you can decide to accept or reject. So there are these accept, reject, clique algorithms. I want to talk to a computer scientist about this because I think these algorithms already exist. You know, that they've in various contexts. They already exist, these algorithms. Okay, but I don't want to build just a clique or a finite clique. I don't want to build just a finite clique. I want to build a clique which, when you enlarge the finite set in a very simple way, it's still a clique. In other words, there's this very basic function I have on vectors called the upper shift operation. The upper shift operation says, take all of your non-negative coordinates and add 1. That's called the upper shift. Take all the non-negative coordinates and add 1. So I want to take one of these standard clique algorithms, non-deterministic ones, and I want to get a clique which remains a clique even if you add all of the upper shifts of its elements. Even if you add all the upper shifts of the vertices. I want it to be a clique. I still want it to be a clique. I don't have a good name for that. I should come up with a name for that. Upper shift preserving clique. I don't know, something like this. Okay, so in other words, I want this thing to be more than a clique. I want it to be a really good clique. Well, you can do that with large cardinals, but you can't do it without. And you can, and I'm talking about trying to do this for any finite number of steps. So the theorem is that that you can do this algorithm for any finite number of steps and still get an exotic clique at the end. In other words, just a clique is easy. You can do a greedy algorithm. But if you want to do a clique that stays a clique if you add all the upper shifts to the vectors, then you can do it, but only with large cardinals. So I just want to tell you the state of the art, pre-published, by the way. I mean, I have written down the proofs so that these are independent. That's next year. But things have stabilized in a good place here. And I think you can get a feel for how this does relate to pretty friendly mathematics and computer science. I mean, they're always, building cliques and doing things like that. You can be my interlocutor, Colin.
You see, I know nothing about computer science. I look at those things and they're interesting to me, but I haven't pursued them. And that's not. I went off and learned the what's his name theorem, the Ramsey theorem, but I haven't pursued research on it.
Okay, but I wanted this to make sense to a general mathematician.
Yeah. It's an intriguing thing. And that's where I wanted to stress that lots of stuff that's perfectly traditional, sensible, all mathematicians like it. Not all mathematicians learn it in any detail.
No, I know that.
Yeah.
But I mean, sections of higher dimensional sets, when you fix some of the coordinates. I mean, just about everybody has to deal with that, right?
Yeah.
Maximality is a big thing. Maximal ideals, maximal this, maximal that, right? It goes back to much earlier periods, right? Maximal objects. Order invariance. Well, lots of invariance everybody does, right? Lots of invariant with respect to some group action or this or that. So this is a particular, very focused kind of invariance, order invariance. And then this clique construction. These are in combinatorics and in computer science.
Yeah.
Well, I get you to be a convert, okay? All right, we have time. We want to move into questions about Colin's talk. And I'm looking. Oh, Lucas, go ahead.
Hello, do you hear me?
Yeah, Lucas.
Hello. Yes, fine. Thank you very much, and thank you very much for your very interesting talks. And I have 2 comments to the lecture of Professor McLarty. The first comment is historical, namely, Gödel never proved the Gödel's second incompleteness theorem. This proof was published firstly by Hilbert and Bernays in the monograph, as I remember, Grundlagen der Mathematik. And the second comment is such that we were warning against the trials of proving of consistency of arithmetic system within the system. Such trial was trial was done, and it turned out to be successful. Namely, I would like to write in the chat. I have written just now in the chat the reference to a paper where the proof of consistency of arithmetic system was actually published, and this proof had been carried out within the arithmetic system.
Mm-hmm.
So this is only my 2 comments to your lecture. Thank you very much. And I recommend the reading of this paper. This is published in Archive, for example. Thank you.
Mm-hmm.
Anybody else have their hand up? I don't see.
Oh. Bob, what do you,
Hi, great talk.
Robert,
oh,
Robert.
Yeah,
Robert.
this is not to tickle Harvey's fancy, but it's back to Hilbert and the anschaulich. If we just move the word slightly, we get intuitionism, and the way that you were explicating Hilbert's concept of the anschaulich really raises the question as to what he thought of Brouwer's program and what the contrast would be to make his notion of anschaulich contrasted with the intuitionist program.
Well, there's some place where I'm very sympathetic to Hilbert. His main response to Brouwer's program was that you couldn't do anything with it. I mean, you could make lots of distinctions and then you couldn't prove any theorems. And this is because you're constantly worried about whether something would be testable or not in some sense. I mean, Hilbert never doubted that every two real numbers are either the same or different. You just couldn't doubt that. And Brouwer can hardly even say it because he hardly even knows what to mean by real number. So I think Hilbert just never thought intuitionism was intuitive at all.
Well, but in some defense of the opposite point of view, I think we can point out that Hilbert was not much of a computer scientist.
No. Even though Poincaré wanted him to be, Poincaré wanted him to get a logic piano, but
Poincaré was not an intuitionist though, but he had some tendencies. He's a predicativist, isn't he?
Well, he's a kind of a predicativist. He certainly doubted that the theory of higher infinities was going to make any sense, partly on what we would now call Levenheim-Skolem grounds, but he can't state them clearly. He did doubt the higher infinite was going to make sense, but no, he was not an intuitionist, and he was one of the first mathematicians to use Cantor's theory of real numbers in a proof in topological dynamics is where he used it. But he was never sympathetic to foundations of any kind. Math was going to be too big for any specific foundation.
So let's see. So ZFC and NBG were pretty much stabilized by 1920.
Yeah. But he died in 1913.
It'd be interesting to see what he would have. Also, I dream about Weil and Poincaré, what they might have made of Kruskal's theorem cannot be proved in predicative mathematics.
Yeah. Now, Poincaré read very widely. If he had lived to 1926, he would have known Zermelo-Fraenkel set theory. I mean, it's just extracting from how he read, but he didn't live to then, so.
Yeah. Right. Did he die young or he died of normal age?
Well, in his 50s. It's not in his 30s, but still young.
It's too bad.
Yeah.
Good to die young, right?
But
Well,
he certainly would have had access to Zermelo set theory. No.
Yeah. Well, yeah. Well, that was pretty well known.
Yes.
Right. Pretty understood. So he never commented on Zermelo.
Well, he commented on the axiom of choice. As I read him, although this is a little bit controversial, what he said was, if we agree with Mr. Zermelo that you can well order the real numbers, but you can never know what the well ordering is, then it's not worth knowing because you can never know what it is. So he doesn't challenge Zermelo's theorem. He just says, what's the use of knowing there's a well ordering if you can never know what it is?
Now, of course, you know, the use of stuff for the finite that cuts pretty well a good instinct, because we know that the axiom of choice doesn't get you any new arithmetic consequences, go back to Girdle. But the large cardinals do. The large cardinals, which are even more esoteric than makes the reals well ordered look like candy.
Yes.
Actually does get you more arithmetic sentences like these here, right? So it's an interesting state of affairs. We need to
Yes.
we need to get these people out of the grave to comment on this. That's what we need.
And I think failing that, I wish that more people would read Poincaré directly instead of read Russell's interpretations of him, and would read his mathematics, and would even, his original French philosophical essays had lots of reference to mathematics, which were cut by the editors for the collected version because they were about math, and who wants to hear that? I think there's a lot of potential for a lot more research into what Poincaré actually thought.
I think it's your turn, Yang Chang.
Oh, okay.
You had a question, right?
Yes, thanks for McLarty for the very interesting, insightful lecture. You have two questions in mind. In the abstract, you claim that Harvey Friedman established the relationship between Gödel sentence and mainstream mathematicals, or just classical mathematicals. Yeah, maybe I missed something in your slide. So, what do you mean this relationship? Do you mean that we saw that Gödel sentence equivalent to some statement in the classical mathematics? What do you mean by this claim? Sorry, can you hear me?
Colin?
Oh, you were asking me?
Yeah.
I thought you were asking Harvey.
No, you're asking Colin, right?
Yeah.
Yeah.
So,
anyway, two of you. Okay. Anyway.
But you were breaking up. So what was it? I couldn't hear everything you said. What?
Just in your abstract, you claim that Friedman established the relationship between Gödel sentence and the mainstream mathematicals. So what do you mean? Do you mean that Gödel sentence equivalent to some statement in classical mathematics?
Well, I mean the concrete independence results, things like the Boolean relation theory, the things he was talking about here. Yeah, I mean we do, and actually, I mean I think this is deliberate, Harvey. I mean I'm sure it is. You're not looking for things that are equivalent to con PA. You're looking for things that are equivalent to much stronger consistency statements.
Yeah, but I am interested, because people keep bugging me. I am interested in watering them down also. What usually happens is I can ask for less invariance. I can ask for less invariance, or I can ask for less nasty functions than the upper shift, and get weaker. It becomes like consistency of something weaker. So I usually can do that. But it starts off with con of SRP, or con of these large cardinals that come up naturally, and then one can actually develop the tools to cut it back. I can cut it back. The idea is I can maybe cut it back to the place where you start to doubt consistency. That's always a funny game, nice game to play. Wherever you are worried about consistency, I'll cut it back right there. See. So
well, I never start to doubt the consistency of anything in ZF, but I am interested in the meaning of consistency. I'm a little disappointed with the Paris-Harrington kind of results, because it's great that they are equivalent to one con PA and independent of PA, but they're not. They're a little rigged. I mean, everybody knows when you insist on that cardinality condition. I would like to know a lot more theorems, a lot more statements in PA that are equivalent to con or one con PA.
Well,
I would like to know a lot more.
Okay, here's the story. Until recently, and even now I haven't actually done the work to cut it back. Until recently, there were no decent pi01 sentences for PA, let alone higher up. Now, these are all pi01. And they haven't been cut back to PA. They have not been. I haven't done that work, but I'm sure it'll follow. But I've also written a lot about PA level 1 con, and it's not that well known. It's scattered all across the FOM and elsewhere, and I think maybe I should, given the fact that people don't realize this. I think maybe I should. For instance, there's a paper with me and Polepsy that appeared recently, Florian Polepsy. Which gives in some ways a lot better than Paris Harrington at the level of PA, of 1 con. There's no trickery involved in it at all. And I've done some other things like that. I think maybe I can send you a reference to it, or I might even make an FOM posting to collect them all, yeah, because they're scattered around, and the only thing that anybody quotes is essentially, essentially almost only Paris Harrington, nearly only, but there is a bunch of others.
Yep. Oh well, Yang Cheng wrote some.
There's also the Kruskal theorem stuff, the finite forms of Kruskal, which can, by the way, be put into PA. All you just have to make sure you use a form of Kruskal, 2 binary trees with no labels.
Mm-hmm.
Yeah, and you get con PA that way. Oh, excuse me, 1 con PA. Mm-hmm. And then I had this new way of not that new, but I had this way of, you can do finitizations, but there's another interesting heavy-handed way to do this. If you take Kruskal's theorem that there's an infinite sequence of trees, one is embeddable in a later one, that's a pi11 sentence, okay, right? It's purely, it's very infinite.
Mm-hmm.
But you can ask this: is there a primitive? Suppose you have a primitive recursive, or elementary recursive, or much lower polynomial time computable infinite sequence of trees. Is one embeddable in a later one?
Mm-hmm.
You can actually see that that's pi02, actually, the way it's stated.
Mm-hmm.
Now, it does mention a computer science concept, right?
Mm-hmm.
It's equivalent to 1 con of PA, or 1 con of ATR naught. It's equivalent to 1 con. It's exactly equivalent to 1 con of where Kruskal's theorem is.
Mm-hmm.
And all you have to do is say, I want the infinite sequence to be heavily computable, low-level computable, and then you don't have to do any finitization.
Mm-hmm.
So,
mm-hmm.
That I did much later than I did the finite, the explicitly, with the estimates. I did much later, and I did put it on the FOM, but I don't know if that's, had you heard about that? I don't think it's that well known.
Well, I don't doubt that I ran across it, but there's just a lot of this, and I don't specialize in it, so there's a lot.
There isn't enough of it. Yeah. Okay, so I think you're right in saying that there's progress going on.
Yeah, and this is something I want, as a result of this conversation, something I want to stress a lot more to philosophers in general. There has been intense, multiple actor interactive progress going on all along on the Gödel theorems. This is not something that's been sporadically developed, and it's not a field where isolated people come up with something. There's substantial systematic progress has been going on, still going on.
Now, do you want to take this time? I would appreciate it if you could just say something about Fermat's last theorem situation.
Oh, yeah. Whew.
First of all, I think I found you agreeing with my conjecture that it's provable in the exact place in which it's stated.
Oh yeah. Oh yeah. Yeah. I'm sure it really is. But you know, I've believed that ever since I knew Gödel's theorems, I have believed that none of the theorems that mainstream mathematicians work on are going to encounter the Gödel phenomenon. And this is not based on anything I knew about any proof of FLT, because there was no proof when I was a student. But I think, you know, the more I look at it, you look at the proofs of Gödel's theorem, and I look at them from my point of view as a fan of Grothendieck. So I'm interested in the upper level apparatus. Lots of mainstream mathematicians say, oh, sure, I cited a book that uses it, but forget that, I don't like that. But even if you do like it, you can see that there's a stratospheric level where the logic is extremely weak. It's all just predicate logic, no arithmetic at all. The stratospheric level where you're doing very weak reasoning, and then there's the arithmetical level where you're doing detailed reasoning. And there's a reason why they're so far apart, although I have proved they didn't have to be anything like as far apart as Grothendieck said they were, right? They can just be as far apart as simple type theory. They don't have to be a universe over ZF. But there's a reason why they're far apart. But none of that stratospheric level is really crucial. And I think that mathematicians, when they hear a talk on some part of the proof, because, you know, people don't give talks on the whole proof, right? Wiles gave one talk on the whole proof. It was 3 hours. It was 3 one-hour talks, you know. But when people hear proofs of parts of it, they relate to how concrete it is, and it is that concrete. But the published form generalizes it to make it quite correct. So I think that, I suspect that there's a fairly direct way to make it concrete that will be EFA, an exponential function of arithmetic. But you know, that's extremely expert number theory, and the less cohomological algebraic apparatus you use, the more expert you have to be. Right? And so so that's hard.
So it's going to be quite a while before that's confirmed.
I think.
But there are these other proofs. I've heard you, I saw you write about them. There are these other proofs that we don't know that they're really better for this or not.
No, they're not really different this way. Kissing has, it's like he's taken the Wiles proof and he's cut it to 1/3 the length, and he's doubled the generality. And then you get a lot of working number theorists who say, well, okay, but I never cared about the whole Wiles proof, and I never doubted the generality. So this is a huge improvement, and it got him a job at Harvard. But it doesn't change the character of the proof, and it also doesn't change how a lot of number theorists see the proof, because they didn't care about the parts he improved.
Now, how does this relate to the other things in number theory like Mordell? Is Mordell something that is proved only at a high level?
Well, it was originally approved using a tau cohomology, which requires fairly high level. And one of the first things people did was they said, you know, you didn't really quite need that refinement. You can get it to what's called the level of Hartshorne. Hartshorne wrote this fantastic book on algebraic geometry. 40 years later, it's still a standard reference. You can do it with what's called coherent cohomology, which just looks like it uses less apparatus. As far as I know, the Mordell theorem, the Falting's theorem, Mordell conjecture, is still proved using cohomology. And there's probably no pressure to go lower than that, because once you've got it at the level of Hartshorne, everybody feels that is already very concrete.
However, with your knowledge and experience, what does that mean? Is it still higher order arithmetic?
You know, I haven't done this work. I suspect that by a fairly routine sort of unwinding, you look at various steps and see, I didn't really need that generality. I could have just said, take something as big as you want without ever saying, let it be the size of a universe. I could have just dumped all that. And I think the coherent cohomology, this is how Hartshorne's book is written. It's written as if you don't need any set theoretic apparatus, except at the beginning of chapter 3, where he says, honestly, if we wanted to make this rigorous, we would define this apparatus. I haven't dug into how much of that you could get rid of very easily. I just don't know.
All right, now these are the two famous blockbusters in number theory that everybody knows about. That's not anywhere near number theory, and they're both probably have verified upper bounds only in higher order arithmetic.
Yeah.
What about the rest of this? Are these guys all crawling around higher order arithmetic every day?
Well, I mean, I don't know most of them. The people I know, some of them are extremely refined about this, and they say no one cares about the issues you're talking about. We only want to prove more theorems in the Langlands philosophy. That's all we care about. Anything else is a waste of time.
Well,
you can have that attitude if you want.
They should actually they have to be sent to logic school a little bit.
Yeah.
But I understand that point of view. But there are. Well, let me ask you this. These people could reduce the logical power of it, but choose not to be interested, or they would have trouble doing it anyways.
I don't honestly know. They would have to learn a couple of new ideas because they don't care. They don't know that stuff at all. I had one prominent mathematician say to me, I don't really know the definition of Peano Arithmetic, but I think, well, of course he could learn the definition if he wanted to, but he doesn't want to, and he hasn't.
Well,
so
you know what? Let me ask you this. Maybe the right way to deal with this is to set up some substantial prizes. That'll get their attention. When they get several years' salary if they do this. What do you think? The idea of setting up a prize fund for low-level proofs of blockbuster number theory.
I'll work on the organizing committee, but I can't donate to the fund.
I'm not. No, we're not. Nobody's asking you to donate to the fund. I'm just trying to say, would that motivate them?
It probably would, because, and the other thing is, a lot of mathematicians while they're in grad school have much broader interests than they're going to have later on.
I might actually be interested in this.
Yeah.
You see a difference between the older and younger crowd in the number theory with regard to these? Well, that's good. And the younger people probably want the money more.
Yep.
So I think we can fix this. I think it would be funny if we could somehow fix this with some money.
Yeah. Yeah.
Maybe the Chinese government would get interested in this. Anyways, I thought this was a great talk, and I was a little worried it was going on too long, but I thought it was exciting to the end. I'm very glad you took. I don't even know if it was legal how long you talked, but I certainly liked every minute of it.
Yeah. Thanks.
Oh, any more questions? I'm still supposed to be doing this. Do I see any more hands? Speak up.
Harvey, is it true for you that our example of a concrete independent statement of PA is equivalent to some metaphysical statements, just like some reflection principle? Is this true for you?
I have never even thought about that. I don't know. I'm very impressed at the central role of consistency statements, and I'm not sure, is that a historical fact because that's the approach we know, or is it somehow intrinsic to the problem? And I like that Friedman theorem that says, yes, consistency strength is the scale of independences. So it's not just that we're used to proving independence by showing it's equivalent to some consistency statement. Consistency statements are the measures. So that's an interesting fact to me, but reflection I haven't thought about.
Any more? Are there any more questions here? No? Speak up now.
sorry. Yeah, there's a question in the chat box. Maybe someone can read for this.
Oh, let's see. I have to stop share to see this. Wait a minute. Okay, I better stop share. Ah, now I can do chat. Is there a reference to concrete techniques of proving G1 or G2? Okay. If you look at the paper that I just took down, in that paper, in my lecture notes, downloadable lecture notes, Harvey Friedman, in the paper I'm talking about, number 78, you will find something related to reference to concrete techniques of proving G1 or G2. At least tangentially related. Oh, not using arithmetization. All right, I'm not sure if this is relevant, but look at the paper 78 on my lecture notes in logic, and I talk about proofs of G2 in there. That's the best I can say.
Yes, I have heard that your comment about the Colin's lecture, and I have heard that paper. But I want to ask Colin that he mentioned in his lecture that there are some ways that don't use arithmetizing, like to use the I remember there's a slide that you mentioned the techniques of using
Concatenations of strings.
Concatenation.
Oh yeah, yes.
I think there's two things there, and I'm not an expert on this, but I'm going to say anyway, and then Harvey can. One way to avoid explicit arithmetization is to do things in terms of concatenation of strings instead. You're covering a lot the same arguments, a lot the same constructions, but you're covering them in a little more intuitive way because you interpret them not just as codes that represent forming strings, but as descriptions of strings. You interpret them in adjunctive set theory. But the other way of avoiding arithmetization is to do more and more in terms of interpretability of theories without asking how you established the interpretability. That's a more substantial change. So there's one where you avoid coding things as Diophantine equations by formalizing the apparatus of discussing strings of symbols. And there's the other where you even get away from that in favor of talking about what theories can interpret what theories, although even there, the way you establish the interpretation is likely to be the Henkin-Pfefferman construction that Visser talks about.
Yes, and of what Friedman said is like in the second flavor. Yes, I want to ask, is there any reference to the first kind of?
All I can say about references on this is that Albert Visser has a web page listing all this stuff, and Harvey has a web page listing all his stuff. I have not mastered this literature at all, but I know two web pages that have it all.
Albert Visser's paper had involved some.
Oh, it's not just one paper. He's got dozens of papers.
Yes, I know. Okay, thank you.
Are there more questions? Speak up. Do you know, I've got a question. Colin, do you know any other branch of mainstream math which really has higher order arithmetic sitting around, if not more, like the number theory does?
No, it's a huge subject. I'm more and more impressed every year at how huge the subject is, and thus how unable I am to answer. But it's amazing to me, the kind of thing that, in fact, you've been insisting on for years. Huge amounts of very theoretical, very elegant math is sort of what you call separable. It's about the countable in some way. Huge amounts of it. Extremely theoretical, extremely elegant, but in fact, it's all what matters is the separable cases. Now, coming out of category theory, I'm very interested in ways of organizing this stuff where you don't keep insisting it has to be separable, because you get a slicker organization if you don't keep insisting that. But the particular cases of interest will be separable.
Okay, so number theory might be unique in this respect, in the mainstream mathematics.
And I think I'm going to sort of cite Barry Mazur here, although I couldn't say a particular thing he's told me. You must expect that because number theory is uniquely the most finely developed branch of mathematics.
Is that right?
Yeah, oh, yeah.
More so than
Yeah.
this differential PDE and differential geometry.
It's
and so
beautifully developed. There's great work on that. There's very difficult theorems. There's impossibly difficult theorems, like the Millennium Prize on Navier-Stokes. Nobody can approach that yet. But
Right.
there is not the continuity of successive geniuses contributing genius techniques in any other part of math that there is in number theory.
Is that what Barry told you, said, or is
He
that?
didn't say it exactly, but I think he'd be glad to hear it.
That's very,
Well, one thing he did say to me is every part of math is number theory. There's just no math that isn't number theory somehow.
well, you say is number theory. What kind of equality relation is that? You mean has number theoretic aspects, or what do you mean?
Yeah, and number theoretic applications. I'll tell you exactly what he said to me. He said, I could be doing finite dimensional vector spaces, and that would really be number theory.
Okay. Yeah, well, if somebody says I'm doing work on the continuum hypothesis, it's really number theory. I think you would have a problem with that.
Well, I'll say it's really combinatorics.
Okay, well, is finite graph theory number theory?
I don't know. I don't know.
It doesn't seem like it, but
I just don't know. I don't know the actual problems of finite graph theory in any detail. So I'm not going to say all of math is number theory, but I am going to say that even though number theory has been quiescent for large periods of the history of mathematics, which, as you've pointed out, the substantial history of mathematics is not 2,000 years since Euclid. But number theory, we have Euclid proving things that are still known today, Diophantus proving things. We have Gauss, Hilbert. There's just there's a succession in number theory of extremely fine insights that even geometry doesn't have, and differential equations certainly don't have.
well, then there's logic.
But logic as a substantial field is a lot younger.
Newer, huh?
What?
Logic a little bit newer.
Yeah, way newer, way newer.
Yeah. Well, it's fascinating. I mean, I was shocked when it became clear that there was something seriously high-powered used in number theory that wasn't eliminable in a weekend. It was kind of, you know, I mean, I was stunned, you know. I assumed the Grothendieck stuff was just for dress.
Yeah.
Well, to some extent it's true, but it's still what remains from what you're telling me is serious high order reasoning.
Yeah.
By the way,
And-
I still beg for you to come up with the simplest possible thing that everybody could dig into because it's so elementary, where the fun begins, the higher order fun begins. You know, we've talked about that.
Yeah.
Where is that? Where is that?
My project there is to go just to the first page of Ribot's paper, which proves the half of the Wiles theorem, where he talks about the absolute Galois group. He talks about complex conjugations on the absolute Galois group. Angus is exactly right to say that ultimately what you care about there are the finite approximations, but the way you care about them is to spend some time talking about the uncountable absolute Galois group. And I would like to just unwind that. And I don't
Now
doubt
you
it.
do realize that's just cardinality C, right?
Yes. Yes.
But you still get it pushed up further, right in ribbit or it's some adjacent stuff. What is it above C? Is it above to the other? No, is it in ribbit or is it all through the other part of it?
Well, it's a lot of the proof right now is organized in categories where you say you take, let me look at all of the, I don't know what, I don't have examples of it on my mind, but I want to look at all the algebras of the following kind. And there are uncountably many different algebras of this kind, and most of them aren't relevant. Most of them really aren't relevant, but you would go crazy trying to pick which ones were. So you say, I'm going to consider the category of all of them, and now I'm going to take this functor.
How many of them are you talking about right now? How many? How many?
Well, I mean, I'm talking about functors between uncountable categories.
Wait,
so now it's a matter of
2 to the C already.
Well, it depends. I mean, once you're looking at maps from one set of cardinality C to another, the truth is you probably don't want arbitrary ones of them, but arbitrary ones of them, that's a big set.
Yeah, well, it's like 2 to the C.
Is it still? Yeah. Yeah, I don't know. I don't have this on my mind right now, but
all right. What I'm trying to say is
probably, the substantial work is, I mean, so here's another thing. I want to look at all algebras over a given field, and I don't want to limit the size of the base. Sure, if I'm going to say finitely generated algebras, now I've got a tight cardinal bound on that. But if I don't want to limit the size of the base, not because I really want arbitrarily large bases, but because I don't want to worry about limiting them. I don't want to specify a limitation.
Then you're buying into higher order arithmetic as a whole. You're basically talking about maybe you can sketch the proof in ZC. Use the extra choice probably. ZC. Is that the place, a natural place to cast the proof?
No, but I've done better than that. I've done it in simple theory of types.
Well, that is ZC.
Bounded ZC.
I mean, yeah, okay. It's too technical for this setting. Yes, bounded ZC.
Yeah, that bounded you can do. And I have done that in the review of symbolic logic.
By the way, you know that we have a meta theorem that anything low down that's provable in bounded ZC is provable in some finite order arithmetic.
Sure.
That is a meta theory. But you can't suck out the number easily out of that. I think you told me that's not an immediate thing.
Yeah, and from a practical point of view, a mathematician who wants to get theorem doesn't see a reason to get a number out of it.
You're right, of course not. Unless they get money for it.
Yeah.
So
there are some communities of number theorists who are highly trained in particular programs, and they can tell you with no uncertainty that their particular program is the only mathematics that deserves respect right now.
But these people tend to think that money deserves respect if you throw enough at them.
Yeah, well, also some of them, the money is just there. They're not worried about it because it's there.
Well, there can always be more. So I'm just trying to figure out whether money is the way to go. But you're telling me that the younger people may be more reasonable.
Well, yeah, but also partly because they're in an experimental phase in their career. I mean, they're going to focus as they move along.
Yeah. All right, so I think I never cease to be amazed at this situation in number theory. By the way, you could experiment with looking at all the decent maps that do that. In other words, cut it down. If you cut it down to the Borel maps or something. I mean, you know what I mean? In other words, you're looking at the full power sets here because you're looking at arbitrary, but use the descriptive set theory tools maybe to start cutting things down, because there's this basic idea that if it isn't Borel measurable, it probably is crazy. I mean, that's a point of view that works pretty well in a lot of math. If it isn't,
but Grundig had an opposite point of view that also worked well for a lot of things, which is that very often you're not just going to drop restrictions to get a more general theory. You're going to drop restrictions because you didn't really use them. You're going to get a simpler theory by working in more generality, because the specificity wasn't ever used.
I mean, the point is, if you want to cut this down to EFA or cut it down to second arithmetic or something, you may well make it harder in ways that these people don't care about, because you're not getting any more information that they care about this way. By the way, I think they're wrong. I think you often get more information, like in the case of Hilbert's basis theorem, right? They had all these things before he did the basis theorem, but then people have returned back to that stuff because it does give more information.
Yeah,
and it's more detailed and doesn't use the abstract machinery. So there's an example where when people finally came back to it, even though it was more work, they did figure out how to suck more out of it. I would think the situation here would be similar, that you could suck out more.
It could. I have not learned computational algebraic geometry. I've looked enough at it to know that there are very attractive and very extensive results in computational algebraic geometry. That's classical algebraic geometry. That's complex varieties. I have no reason to doubt that there's a similar computational field in étale cohomology. Right now, very few general theorems are really proved in étale cohomology. Almost everything is done by taking approximations using what are called spectral sequences. You almost never compute an étale cohomology group. You compute an approximation to it, and that gives you your results. And you see the same thing. You look at just ordinary algebraic geometry of manifolds in 1905, 1910, there were not many examples you could compute. Today there are. But that's the situation in étale cohomology right now. You almost always just go for a germane approximation and say, therefore this theorem is true. You almost never actually calculate the étale cohomology group. Well, that'll change as people get more experience at doing it and get a library of successful techniques.
All right. Anyways, it's a fascinating ongoing story. It doesn't look like it's going to end very soon, about the logical status of number theory. It's kind of fascinating. In the large, this is in the large. In the micro level, I'm trying to write some stuff on the FOM. I have a feeling that there's a micro proof theory where you really dig down deep into much more elementary things. What kind of complexity of induction are you really using here and there? More detailed than normal, like in Hayek-Pudlak, more detailed. There's this delicious open problem. Infinitely many primes, can that be proved in bounded arithmetic? That's still open. There's this micro stuff in and around number theory.
Yeah. And the reflection of that I'm familiar with is theorems on really how prime gaps. How much can you limit prime gaps? Well, that's relevant to whether you can do it in bounded arithmetic. And it's a very hot research subject.
Well, right. The almost twin prime conjecture.
Yeah.
I mean, the stuff goes back to Bertrand's postulate, right? The prime between n and 2n. Stuff like that. Well, maybe number theory is good. Yes, I think maybe.
Number theory is good.
A strange situation, but I never thought of it that way. That in some sense it is got things going for it in depth that the other mainstream branches don't quite match, right? I think that's pretty interesting.
Well, as a historian of math, I can say, going back to Euler, you've got a tiny number of excellent mathematicians saying that number theory is far more beautiful than most people know. But that's beauty. That's a different concern than you've got. But it's always attracted the very top people, even at times when it hardly attracted anyone, except the best.
Well, piano playing also it has its merits. It's more beautiful than most people know.
Yeah.
And it has attracted strong people, piano. Yeah. So piano and number theory, I don't know if we can make much of a connection yet.